Hi everybody, part N. We're getting up there now. Um, this is the introduction to cloud computing. I'm your instructor, and it's big data / data engineering. And this discusses a pretty interesting area, but sort of fun area, clouds and parallel computing. And we do our classic parallel computing described in general. This dates from 1980 or so. We compare big data and simulations, and we discuss what's hard, because there's quite a big difference between the different classes of application as to how easy or difficult they are to do. So, and we sort of try to stress that actually a lot of the reason why clouds have been so successful is they focused on the easier problems, as they ought to, because you need to do those first. But there are some problems that are hard. All right, so what is the essence of parallel computing? Well, you always remember I told you the difference between data and model. Well, both of them actually can be subject to parallel computing. You have the data processed in parallel and or the model processed in parallel. And so you take the data and the model and you use some heuristic or algorithm or something to divide the data and model into parts. The way Hadoop and Spark do it is sort of trivial. The data is numbered from 1 to a billion, and you just take the first million and put it in one processor, and so on for the next 1,000 processors. Each gets the next 1,000,000. So it's a really simple decomposition. It's what we would call the one-dimensional decomposition. You label the points in a line and chop the line up into parts. In the more sophisticated approaches, you do much cleverer ways of dividing it up in ways that are designed to minimize the overheads and things like that. And that particular simple approach of putting them in a line is rarely the best. And we give some examples of particles in cosmology, simulations, chess, computer parallel chess. These are how it used to be done before deep learning existed, how to process missiles, where maybe that's getting more topical, how we process tweets, DNA fragments, documents. They're all done actually in the same way. You identify a space, and you take that space and chop it up into parts, and you make certain that each computer or process or thread does its part. And we typically use what I call the owner computes rule. Namely, the process that owns particular data computes for that data. And we also use the single program multiple data model because we've chopped up the data or all the model parts. Actually, you sort of even see in that SBMD that D is misused. It's really actually, as originally invented, D was model parts. It was not data at all in the fashion we use data today. So in SPM model parts, we have single program, multiple model parts or multiple data parts, and that means that the same program is used to analyze part of the data as used to analyze the whole data. And that's usually what's necessary, because you build into your program the capability of doing the analysis. If you're doing 1 billion data points, the way you analyze the first 1,000 is going to differ in that the first 1,000 data or first 1,000,000 data points are different from the next 1,000,000 data points, but the algorithm used is the same, and so the computer program is the same. So that's why SBMD is pretty important. Okay, here is an example of simulating cosmological clusters, and here is a picture of the universe. And the feature of cosmology and actually astronomy is the density of particles, whether they be stars or actually galaxies, is varied dramatically. That's due to Newton's law, which attracts particles. So you have hugely dense things, and the densest is probably a black hole, or in the case somewhat somewhat less extreme case in the galaxy, our galaxy, where we do have a black hole in the middle. That's probably incredibly dense, with lots of particles sucked into it. But there are also things like globular clusters, which are groups of stars which are quite close to each other. And so when you try to do parallel computing to evolve our galaxy or to evolve our universe, you have to pay attention to that. Because when the particles are close together, you really have to do an accurate calculation of the force. But when they're far apart, you can actually take all these particles here, lump them together at their center of mass, and calculate the attraction to the particles here. So actually at long distance, you can do very simple, fast calculations. But when stars are near each other, the details matter. It matters whether the star is very close or pretty close. And so the number of processors needed to simulate this part of the galaxy or universe is much larger than is needed to process this part, where the stars are denser. Sorry, the stars are exactly the opposite of denser. They're less close. They're less close together. They're rather low density, and so you can do. And also, so it doesn't just change the number of data points; it changes the work per data point. Because if you have a star and there are lots of stars near it, you have to calculate the force by summing up all those stars. And so we have to do a decomposition with not even equal number of stars per point per processor. You have to do equal amount of work per processor. That's sort of there are various ways of doing this. Here is a very old slide. This must be from the early 80s, about different ways of thinking about this general problem of chopping up stars, or here these points. And I took only 4 processors, and here is the sort of typical so-called domain decomposition. You take your points and you do geometrical shapes, and you try to divide those shapes into equal number of points, 21 particles. Now actually it's all wrong, because the points here partly require more work than the points here, but let's ignore that point. But it is at least load balanced. Every processor has 21 particles. And at least in the case where we do, where we don't have different amount of work per particle, that's optimal. But the trouble about that particular approach is these particles will move, and they will cross boundary lines. And so these boundary lines have to be recalculated every time step. And that can be time consuming and very messy. So you have to remember the Euler compute rule. So when this particle moves into the domain of processor, from processor 1 to processor 4, well, you better do something about it, because it can't be kept in processor 1, because otherwise, when processor 4 is calculating for that particle, it has to actually do a memory access to data on processor 1, which is costly. So this one is only optimal at each time step, and you have to change it. And so sometimes that's done, and that's a perfectly reasonable algorithm, and there are people who've done that algorithm in a very brilliant fashion. Here is a cruder method, which is an example of a different way of looking at it, which is not perfect, but is much more robust as the particles move. And that's a so-called block scatter decomposition. You take the numbers 1, 2, 3, 4, write them in a square, and you just replicate that square. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. This gives you the block scatter decomposition. And then you look at processor 1. It's no longer got all the particles that are geometrically close to each other. It's scattered over processor 1 is scattered over the whole domain in which these particles live. And the advantage of this approach is as the particles move, well, they just move. When particle moves from, say, this point here to this point here, then it just moves from 1 to 2, and 2 is in charge of that domain, and there's no need to change the decomposition strategy. Whereas in this case here, to keep the optimal decomposition, this decomposition would have to be changed. And so the block scattered is very robust. The algorithm doesn't need to be changed as you evolve in time. And the only disadvantage is not optimal. Namely, the particle counts per processor are 28, 19, 21, 16. So there's almost a factor of 2 variation. But still, this will actually get you parallel speed up, and it's super robust. And with a real problem which is bigger, you will probably be able to do a version of the block scattered decomposition, which was more had a better performance than the factor of 2 between the smallest and the largest processor point count. All right. In my early days of parallel computing, we worked for the so-called Strategic Defense Initiative, which was trying to understand how to track missiles in parallel, and we did similar type of decomposition. Here is a possible enemy country, and it has missile sites here, 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 and here. So we would just assign processor nodes separately to each of these missile sites. So with 4 processors, and maybe actually there were 2 missile sites in this here, and 2 here, and 3 here, and so on. We were able to use a simple parallel algorithm of decomposing the sources of the missile sites or the positions of the missiles in the sky to processors, and we got a very efficient algorithm. So in the case of, so this is decomposing, in this case there are 2-dimensional domain for the, we're decomposing missile sites. If we're decomposing missiles, it's probably 3-dimensional. But in any case, it's geometric, and it's definitely never 1-dimensional. So this algorithm of Hadoop, just put them in a line and chop them up, is not the right algorithm. You need to look at the geometry of the problem. So when you do decomposition, the space that you're working in counts. And you need to do a different algorithm in a different space. Now, an interesting space is that of the game tree. So here is the computer game tree. Computers, what typical first move is pawn to king 4 or pawn to queen 4, e4 or d4, and so on. And of course there are lots of other moves, c4, f4, what have you. And then you have to look at all the possibilities of black and so on. So this is the space of the chess problem is a tree, not a geometrical space, and you need to decompose that tree and do a parallel algorithm over the tree. And so actually trees are harder to deal with than geometry spaces, and algorithms with like graphs, which involve trees, tend to be the hardest. So, but they're doable. I mean, this again was very early work, and nowadays computer chess is done differently, more efficiently. Deep learning's involved, possibly. But we actually entered the computer chess championship and did very badly because our computer broke. Cusses. But we had actually probably had the best algorithm there was, because we were focusing on a parallel algorithm, and we used an early parallel computer, and it wasn't as reliable as the other computers being used by our opponents. So we messed up, but we tried valiantly, and we actually wrote some reasonable papers on computer chess. Okay, so I like these slides here. These are very old. These slides came because some newspaper person told me to explain parallel computing. And then I pointed out to this person that something I already mentioned, that parallel computing and society are pretty similar. Society is organizing people to solve problems, defending the nation, building a car, driving a car. You're solving a problem which is a parallel problem with multiple people involved in it, and that's parallel computing. We know the hardest part of society is getting people to agree, coping with their egos and things like that. And organizing the problem over these multiple people is really hard. That's what managers do. And we know managers are important. Now, in the old days, in fact, in the comics, we would not do this. We would just have Superman or Superwoman, and we would not use a team of lots of people. It's much easier to solve with one man or one woman. And so we then introduced this example, Hadrian's Wall. And here's you can see how old this figure is. It was again in the early 80s. And here's a picture of a wall. Hadrian was a Roman emperor who built a wall between England and Scotland. I was born in Scotland and lived in England, so it was a nice thing for me to consider. And here are these bricklayers. They're laying the bricks to build the wall, which is like the Great Wall of China. It's just a different wall. It's not impressive as the Chinese wall, but it was historically quite interesting because the Scots were pretty unruly, and the Romans in England wanted to have a good time. So they built the wall, and they almost certainly used parallel computing. They did not have one bricklayer. They had lots of bricklayers, probably slaves, that they'd roped together to do this problem. And you can see these people are laying bricks in parallel. So walls can be built in parallel, and there are obvious constraints. Like if you have two bricklayers, they better be at roughly the same height, or else it's going to look pretty silly. And also, you can also tell what the key issue is. Namely, there's a typical length there, which is the size of the wall, which is actually rather smaller than will be in practice, assigned to a particular bricklayer. There's another length, which is sort of the overlap length. They're going to interfere with each other over this length. And if you look at how well this works, technically, you need to have this distance, something which is not true in the diagram. You need to have this distance, L, the size assigned for each bricklayer, to be much bigger than the overlap. Because otherwise you will be, because you're going to be screwing around and having bad performance when the bricklayers are at a distance L overlap between each other. And in this diagram, they're always going to be interfering with each other. So it's a catastrophe. Well, not a catastrophe, because hardly building a symbolic wall is not going to give anybody any heartburn. So this is an 8-person parallel computer, where each computer is one person. This is a linear decomposition. This is the Hadoop decomposition. We've taken the line which is the course of the wall, and we chopped it up into parts. So this is a one-dimensional decomposition. If we did the same problem for putting down building the floor of Hadrian's palace, that's a 2-dimensional problem, because the floor is 2-dimensional and is not 1-dimensional. And we would have the same issues, but we need a different decomposition, because we would not be able to easily map the floor into a 1-dimensional line. So we want to make parallel computing pretty efficient, which says that if we look at the time for one processor over the time for n processors, that gives us a speed up. We would like this number to be big. Then the n processor time is small compared to the one processor time. And Amdahl had a law which said speed up was limited. But actually, that answer was wrong. Speed up is not limited as long as we have big problems. And so like here, I say L has to be 60 meters if the overlap is 6 meters. If we have things of the same size, which is essentially the problem Amdahl was looking at, then we have what people in England would call too many cooks for the broth. And if everybody is sitting there, so if you have too many cooks, it's not so easy to use those cooks in parallel, because there's a lot of detailed coordination work on cooking a dinner. All you can do is you can have multiple cooks in multiple restaurants cooking multiple meals, but you can't have 60 cooks in one restaurant, in one kitchen, cooking one meal. That's much harder. So this is a fundamental principle. If the problem is big, 600 meals in 60 restaurants, 10 meals done at a time, that's a biggish problem. You can use lots of cooks, maybe 60 cooks. However, if you have If you want to do one meal in one restaurant, you can't use 60 cooks very easily for that problem because they'll all be interfering with each other, and it's not a small problem. So speeding up small problems is much harder than speeding up big problems. But it's okay, we're in the big data world, so the data's big, so it's going to work. We're unhappy, this key criteria is satisfied. Here is a neural net, and so that's good. It's nicely parallel. We have all these neurons linked with axons and dendrites and so on. And I pointed out this is even using messaging, which is how we would do it in a real parallel computer when we have our processors talking to each other to do coordination. Those coordinations done by messaging. And we also have pretty interesting hierarchy. This is the low-level neurons connected with messaging. At the higher level, we have brains. And the messaging is really slow because brains are talking to each other, discussing how to do things. That's a really inefficient parallel computer because the ratio of the time to do computing, which is the time the brain takes, that's very small compared to the time it takes for you to listen to my voice. Really inefficient. The information processing of the brain is very, very fast, and far faster than the information processing of my voice. If we look at anthills, then we have a bunch of ants which are smaller brains, and they send and receive messages again by chemical signals. So all nature's computers use message passing, and there's plenty of different architectures, and I said web services or services are just message passing. Everything is message passing. All right, so if we look at the classic features of parallel computing, then we will find that we have SPMD, we have maps, which are, in the case of simulations, doing this, say they're doing weather simulations, there'll be mesh points divided up, and usually geometrically in 3 dimensions, and they all be sending little messages to each other to make certain the processors doing the computing in this part of the weather can talk to the processors doing computing in the neighboring parts of the weather. And often you use what's called a capability job, which is a giant job, which can actually use up to 100,000 cores on the same problem. And you run these in batch mode. Jobs take a long time, and these machines all run at 100% utilization. They're very fault fragile. And if one node breaks, the whole system breaks. And all the maps take the same time, because otherwise they have to wait. If you have 100,000 cores and one core is slow, you're doomed. Can't have that. All right, MapReduce is different because you can have stragglers, because all the stragglers mean is you just have to wait for the final answer, because if you have 99 processes and they all finish, one process takes 100 times longer, well, you just wait for it to finish. Those 99 are finished, you can reuse all those nodes to do something else. Whereas in the case of parallel computing in general, you cannot do that because the nodes have to do something, then they communicate, and then they iterate and come back. So iterative problems are much harder because you can't give up the nodes to be used by somebody else. And we've already pointed out that pleasingly parallel or map-own is a special case. And then we have iterative MapReduce, which we showed as is the style 3 of the various 6 types of MapReduce in an earlier slide. And that caches results and supports classic SPMD parallel computing with pretty reasonable, with messages being sent back and forth between the nodes. So that's, and as this is linear, this is classic parallel computing for linear algebra, and most machine learning uses linear algebra. So big data, you would think big data would need high performance because that's what big means. Big is high. So of course, although we talk about high performance computing, we could talk about big performance computing, And obviously, big data needs big performance. And so using HPC, big data should run faster. This concept is called hyperscale, and is a transformational technology according to Gartner. And but it's a little more subtle because maybe the big data processing involves lots of input-output, there's a lot of distributed data, so quite how you accelerate that is not so clear. We have all these pleasingly parallel jobs in the big data field, like processing data from CERN. This is the Large Hadron Collider, which is the big CERN accelerator. And these nifty HPC algorithms aren't used because you do what I call local machine learning. Every event taken by the LHC, and it does billions of them, are processed independently. A slightly more subtle case is MapReduce. In fact, the LHC processing is MapReduce when you classify it properly and do the full algorithm. However, the largest part of LHC is map only, and that dominates over the reduced stage. Here's an interesting comment from Andrew Ng. He noted that every leading machine learning group must have deep learning and HPC excellence, because deep learning is HPC intensive. And as I've noted before, things like topic modeling, clustering, dimensional reduction, graph algorithms, they will involve a mix of map collective, map point-to-point, and they all have an iterative structure and they benefit from HPC. And when you use HPC technologies like MPI, the message passing interface, you run 10 to 100 times faster than classic big data technologies of Hadoop, Spark, Flink, and Storm. Well, if we look at the pleasingly parallel jobs now, then we have parallelism over users and usages. Namely, a usage model is the long tail of science. We're gathering data from lots of environmental sensors. And that sort of contrasts with big science, when a single accelerator or a single satellite is gathering data. And those actually gives huge amounts of data sources. You actually split up the data. In the case of environmental science, the data is already split up. And these are typically associated with individual researchers. Every researcher has 1,000 things which they're deploying. So you get lots of things and lots of researchers. And clouds are very suitable for this problem. And there's often a map-only use, or possibly some MapReduce, because you want to summarize and collect together results of the different maps. So, and then the difference between users and usages is probably best illustrated by search. In the case of a search, you can parallelize the search. That's the usage. Because you can search over independently over all the different websites, all the different collections of websites. But each user can also run a separate search. So when you're on Google, you actually have two forms of parallelism. Lots of users simultaneously searching, and each search can itself be done in parallel because you're looking over the entire set of data. And that data can be looked at independently and collected together. And so the exact choice of the parallelism, users are always going to be parallel. You can choose how you parallelize the search and how many nodes you run every search over. Here is a sort of cosmic summary of parallel computing for big data. And it just says everything is actually using the same basic idea. You're chopping up the model parts or the data parts. You're using one-dimensional, two-dimensional, multi-dimensional, super dynamic, super decompositions. And so you break the data or the model parameters into parts. You put each part into separate nodes. You use the owner compute rule, leaving the data untouched, but changing the model parameters. These computations called a map and MapReduce is called the computation in MPI. And if you're doing pleasingly parallel, then that's all there is, except for managing the whole process. If it's globally parallel, namely you're doing a clustering, and you spread the data set over the nodes, and you spread the centers over the nodes, then you have a truly parallel algorithm which requires significant management of communication and the nodes have to communicate because each are part of the problem. Then you use a particular communication mechanism, TCP, RDMA, native support of a high-performance network like InfiniBand. You're going to use different communication styles, point-to-point, collective, or publish-subscribe. I described the issues of load balancing for the galaxy problem. Sometimes the best way to chop up the problem varies with time, with the data, and in the case of the galaxy simulation, the particles are moving around, and so the best decomposition changes with time. So you can have a fixed task with data fixed or data flowing between tasks. You can have an automatic parallelism like Hadoop, or you can have very customized parallelism where the user designs a sophisticated algorithm. We have different various algorithms. It can be decently parallel, which is simple, or complicatedly parallel. We have to worry about fault tolerance, and how the data's output is also needs to be discussed. But these are all roughly the same in all problems and all approaches. And what appears to be big differences are usually either mistakes or more often they're just a different type of problem. If somebody is doing a pleasingly parallel or a MapReduce problem, they can do things in a very different way from somebody who has to do a large-scale weather simulation. All right, the last slide of this lesson is rather complicated, and it sort of lists a whole sort of technologies, approaches, commodity clouds, which are sort of the old-fashioned clouds, lots of rather low-power computers without lots of high-performance computing. We have clouds that deep learning has really accelerated interest in, what you can call HPC clouds. They have GPU accelerators or possibly high-performance interconnects. And at the over here we have supercomputers, which you view as yet another variant of an HPC cloud. And if you look at the vertically, we're looking at sizes of data. So here we have a lot of data, and here we have a little data, and here we have what's to me what I studied, the size of the synchronization constraint. When you have these jobs running around in parallel, which have to talk to each other to synchronize themselves, then the size of the synchronization goes from loosely coupled to tightly coupled. Here we have tightly coupled. And traditional simulations on exascale computers, they're traditionally tightly coupled. And that's what supercomputers are aimed at. They're focused on solving that problem. If you go to a traditional commodity cloud, it actually doesn't have much synchronization at all. MapReduce is very weak synchronization. And there are even no synchronization at all, map only or pleasingly parallel problems. This is the major big data computing thing over here, loosely coupled, largely independent jobs. And that's why they look rather different from supercomputers, which are large jobs, lots of parallel things, and tightly coupled. But there are actually big data problems of this category. If you look at latent deletion allocation or graph analytics is probably more tightly coupled than any simulation. In the simulation area, you talk about sparsity and adaptivity. So the more adaptive you are, changing in the course of the computation, more sparse you are, or more irregularity there is in the sparseness, that's what really counts, then that makes the problem much harder. In the middle here, we have classic ImageNet deep learning, which is done with full matrices. And it's got linear algebra at the core. With linear algebra, we know how to run. GPUs run real fast. That's why they just go like a bat out of hell and really can do these amazing things. And then, of course, as we say here, these are just two characteristics, but they're pretty good characteristics. And even at the big data, we have, here I have parameter sweep problems, where you're actually doing simulations, lots of them, probing a space, and those parameter sweeps have low data, of course, but they're still in this commodity cloud thing because they don't require any synchronization. All right, so this is, I think, a reasonable good way of synthesizing everything together and realizing that There are similarities and differences in all aspects of big data and simulations. Thank you very much.